The angiojet system is a percutaneous mechanical thrombectomy device that rapidly extracts thrombus and other debris from the arterial lumen. It is the only currently approved thrombectomy device for use in native coronary vessels. In this brief presentation, we'll see how the angiojet system generates powerful hydrodynamic forces in a unique way that allows for highly effective thrombus removal with an excellent safety profile. Angiojet technology takes advantage of the Bernoulli effect, a basic principle of fluid behavior which was discovered by Swiss scientist Daniel Bernoulli in the mid-1700s. The practical consequence of the Bernoulli equation is that as the velocity of a flowing fluid increases, its pressure decreases. Where the velocity is greatest, pressure is lowest. The Bernoulli effect explains, for example, why a shower curtain moves toward the water jets. The rapid flow of water past the shower curtain creates a negative pressure that pulls the curtain inward. Angiojet utilizes high-velocity saline jets to generate very strong negative pressures. Saline is pumped to the catheter tip, where the jets are directed backwards at a rate of 360 miles per hour, reducing local pressure to less than negative 600 millimeters of mercury, a near-perfect vacuum. These powerful vacuum forces, in combination with angiojet's cross-stream technology, allow it to efficiently extract thrombus through a combination of four effects: entrainment, capture, fragmentation, and evacuation. Cross-stream technology describes the complex network of fluid currents generated at the catheter's inflow and outflow windows. These currents loosen thrombus from the vessel wall and draw it toward the inflow windows, a process known as entrainment. Due to the Bernoulli principle, thrombus is captured within the inflow window. Once inside the catheter, thrombus is fragmented by the high-velocity jets into microscopic particles that are quickly evacuated from the body. These jets are fully enclosed by the catheter to prevent damage to the vessel walls. Let's contrast this with manual aspiration. Drawing back on the syringe plunger creates a strong negative pressure at the syringe tip, about negative 600 millimeters of mercury. Due to frictional losses, this force markedly decreases along the length of the catheter, so that at the catheter tip, it is only 5 to 10 millimeters of mercury less than systemic pressure, resulting in a very mild vacuum effect. We can see here why angiojet thrombectomy is superior to manual aspiration. First, manual aspiration generates a much weaker vacuum force, requiring that the catheter tip be immediately adjacent to the thrombus. This hydrodynamic model compares the intraluminal flow velocity patterns generated by angiojet versus manual aspiration. It confirms that due to the much higher intracatheter negative pressures generated by angiojet, a much larger area of fluid flows is created that effectively draws in embolic debris. Second, if the aspiration catheter tip is too close to the thrombus, it can easily occlude. Angiojet's powerful fragmentation effect prevents occlusion of the catheter. The severe limitations of manual aspiration were demonstrated in a 2003 in vitro study. Manual aspiration resulted in 6 times as much residual clot mass compared to rheolytic therapy with the angiojet. A second study by Roberts and colleagues also demonstrated that angiojet was superior to manual aspiration in removing macroembolic debris. It also showed a 6-fold difference in effectiveness. In summary, manual aspiration can remove some thrombus but has major limitations. Angiojet technology utilizes rapid saline jets that generate a strong vacuum zone via the Bernoulli effect, drawing in thrombus and debris. The jets then fragment and evacuate the particulate matter, resulting in rapid and safe thrombus removal.